Hello, good morning.
Okay. So our next talk will be about vibration monitoring. And vibration monitoring is surely essential for condition monitoring and predictive maintenance. So I'm happy to introduce our next speaker, which is Vladimir Janousek, who is an application team manager at ST Microelectronics. And yeah, I think Vladimir is ready. The crowd is ready, so have fun. The stage is yours.
Thank you, Joachim. So thank you for the nice words at the beginning. I would like to mention our company a little bit because maybe there are some people who don't know us. So ST Microelectronics is a European semiconductor company. So basically we are designing and producing chips. So semiconductors which are used in the devices we can see around here on the trade show, of course. And as part of our product portfolio, we are also designing specific sensors in the area of microelectromechanical systems, so MEMS sensors, basically. And today in my speech, I would like to touch the latest one, which we released for vibration monitoring or condition monitoring of mechanical elements like bearings, which you can see in the picture. So before I deep dive in what we can offer in our new product, I would like to start with a little bit of theory, because it's important to set the stage and to position the new sensor we are introducing into the mechanical systems. So what you can see on the left side in the picture is a water pump. So typically what you have in the water pump is, of course, the motor. There are some mechanical elements. And in the system itself, there are different parts of the mechanical element which are generating different frequencies, which you can see in the waveforms below the motor. Typically, in case we have some unbalance or looseness on the motor, we are in the entry range frequencies, let's say typically up to 2 kHz. For gearings and starting for bearings, we are in between 2 and 6 kHz of vibrations typically. But if we want to go deeply in the specifically bearings, we need higher bandwidth vibration sensors. So this is where we are focusing with our new component. Second part of this slide is the typical PF curve. So it's basically the potential failure and then the failure of the mechanical, let's say, equipment in its lifetime. So you can see on the horizontal axis the time. And basically, as the time is increasing, the mechanical element or the system is degrading. And if some parts of the system are starting to degrade, you can observe, for example, the ultrasound coming from the system, the vibrations on which we will focus on. And then, of course, if you don't repair particular elements in the system, you can start to hear the noise, you can see increased temperatures, and after the smoke from the machine, there is a failure. So this is basically the theory for the vibration, and now I would like to focus a little bit on the bearings specifically. So in the bearings, there are some, let's say, typical defects which are, let's say, resulting in vibrations, and those are linked to so-called characteristic fault frequencies, which are linked to ball frequency, for example, on the outer layer or the inner layer of the bearing, or it can be linked to the spinning of the ball, stuff like that. And of course, those elements, the small parts, are generating specific high frequencies. So we have specific high signatures in the frequencies. There are some modulations and harmonics in the system. And the challenge for our customers is how to, let's say, capture those defects. So ideal in their application would be to embed the sensor directly in the bearing and to make the real-time measurement. And this is what we are trying to target. Real-time, high bandwidth, and of course low-noise sensors, which would be suitable for such application. You may ask me what could be the challenges for a, let's say, sensor in the bearing. So I tried to list out some of those. So take them as the, let's say, key performance indicators for such sensor. So the first one is, of course, the bandwidth, because I told you there are really small elements in the bearing which can generate really high frequencies going to tens of kilohertz. And our aim is to capture those small changes as soon as possible, so as early as possible. Another aspect is the measurement range. So you would be surprised how high the measurement range can be. It can result in tens of G of accelerations when there is a problem in the bearing itself. And this is why we are also proposing higher range acceleration sensors. Typically, this application is also occupied by piezo sensors, and this is typically very costly. So it's also important to focus on this aspect, and fortunately, the MEMS technology is offering, let's say, the system integration, and the cost aspect is also much better compared to the piezo sensors. Battery lifetime, okay, if we have fully integrated system inside the MEMS sensor, we can significantly reduce the power consumption, and we can have the system running on the batteries. And the last point is linked to the temperatures. So typically, if you are really close to some moving elements or at the bearing or in the motor, the temperatures can go really high. So you need also a suitable component to sustain this high temperature range. A little bit of comparison, because I touched the piezoelectric sensors, so I would like to compare them to the MEMS sensors. So in this graph, in blue, you can see the advantages of the MEMS sensors, where in the red, we have the piezo sensors. So with the latest sensor I will talk about later on, we are more or less touching all the pros which the piezo sensors had, so which is the frequency response and the full scale. And we are coming very close to the noise level, which is, let's say, offered by the piezo sensors. So it's also mentioned here. So we are at this level, 35 microG per square root hertz noise, which is very good. On top of this, our benefit is that we can pack the MEMS device in a very tiny package. So compared to piezo sensors, okay, we are in the 4.5 by 4.5 millimeter package. And of course, what I mentioned already is the sensor and system cost and the power consumption. So now let's have a look on the, let's say, portfolio of our vibration sensors. And what you can see in this chart is that basically we have 4 different, let's say, ranges of components which are suitable for different applications, which are differing in the, let's say, frequency bandwidth they are capable to capture. And the new device we are introducing to the market is going above 10 kilohertz of bandwidth. I will detail this a little bit more. And this is exactly the area where we are capable to really compete for the, for example, bearings monitoring versus the piezo sensors. So what are the advantages of this sensor, the IIS3DW10IS? First one is linked to the wide bandwidth. So you will see that on X and Y axis in the 3D MEMS structure, we are able to go up to 15 kilohertz of bandwidth, and for the measurement range up to 200 G. So you have selectable, let's say, ranges from 50, 100 to 200 G, depending on your application needs. And second, very important point is that on top of the vibration sensor itself, we are also integrating a risk core. So you can program in the sensor your own algorithms. So for example, you decide to program FFT inside the sensor. So you want to calculate on the fly the frequency spectrum in the sensor, you can do it. And you are just getting out the results of the FFT. Last point, very important for the vibration sensor, is the temperature range. So with this one, we can go up to 125 degrees. And also not negligible parameter is the longevity. So we are committing from today, when the device was released, at least 10 years longevity. So it's very suitable for industrial long-time applications. A little bit more about the sensor. I will not mention what I was already describing, but what I want to also highlight is the power consumption. So the typical power consumption depends on the, let's say, setup of the sensor. So it has 3 orthogonal sensing axes, which you can enable or disable based on what your application needs, and you can scale down the power consumption. Typically, such accelerometer in the, let's say, IoT application is not running permanently. You are switching it on for a very short time, few times a day, and you are processing the data directly in the embedded IPSPU, and then you are, for example, sending to the cloud only the results. The package I mentioned already, just to maybe highlight that for the Z-axis, which is the third axis in the package, the typical, let's say, bandwidth is a little bit smaller because from technology point of view, the Z-axis in the MEMS structure is done in different way compared to the X and Y axis. I was mentioning the embedded RISC core, and basically here are some examples of additional, let's say, algorithms which typically our customers can run in. What is the most important parameter of such sensor? Or if I would like to sell it to you, the first thing you will have a look at is the frequency bandwidth in which it can operate. So I prepared one slide, which is, let's say, comparing our vibration sensor frequency plots versus the traditional, let's say, analog output and piezo sensors. So what you can typically see in those devices is that you have flat frequency response up to certain, let's say, frequency, and then there is typically resonant peak, which is taking few dBs in the amplitude, which is something you have to deal with in your application, of course, in case you are really interested in the amplitudes of the vibrations. What we did in our sensor is a specific design where you can see that in the digital part of the sensor we are attenuating this peak. So what you are getting is a really flat response up to the -3 dB range, and then the signal is attenuated. I will show you the filtering chain later on in the block diagram. So as you can see, for the X and Y axis, we can go, let's say, up to 15 kHz. For the Z axis, typically 12 kHz bandwidth. Other aspects which are important for the sensors and which I was explaining are linked to the noise, the sensitivity versus temperature, and also the bandwidth in the versus the temperature. So let's start with the noise. So the noise value you can see in these charts. We are typically providing them in the data sheet, so every customer has access to it. And you can see that for, let's say, 50G range, the typical noise is in the range of 35 micro-G, as I mentioned before. For the Z-axis, it's quite close to this value as well at 50G. What is more important and what is, let's say, the innovation in our sensor is also the impact of the temperature. As I mentioned, the sensor can go up to 105 degrees, but we are starting at -40 up to 125. And we are, for the sensitivity, guaranteeing ±2% of accuracy over the temperature range. And what is also very important, and which is a little bit bigger benefit versus the piezo sensors, is also the impact of the measurable bandwidth over the temperature. Again, from -40 to +125, we are quite well in the, let's say, variation of ±1 kHz. So you can easily measure, let's say, for the X and Y, up to 14 kHz over the complete temperature range of the sensor. So how we achieved this innovation? It was not in our previous generations. I will touch a little bit the technology we are using. So the technology we are using in our company is called TELMA technology, and it is the technology how we are creating the 3D structures in the silicon. So in the typical, let's say, MEMS technology, you have one buried polysilicon layer and one epipolysilicon layer. What we brought in our new device is so-called TELMA double technology, where we are bringing one epi layer more in the system. And this allows us to exactly improve the sensitivity and also to play with the noise level and so the accuracy of the sensor. Okay, I think this was enough for the technology, and I will focus a little bit on the digital engine. I didn't mention that the sensor is fully digital yet, and I did it intentionally because I want to touch it now. So basically, in your application, when you try to use this sensor, you are using SPI interface or I3C interface with your microcontroller. Okay, filtering block. We have the MEMS element I was showing on the previous slide. We have the ADC converter to get into the digital world. And then there is a set of, let's say, digital low-pass filters, which you, as a user of the device, can program basically from the microcontroller. Then, to get the data out, you can get them directly through the output registers or through a FIFO, or you can pass them to the internal RISC processor at the same time. So you have the data available outside, but also for the internal processing at the same time. The full chain block is visible here. Okay, so I was talking up to here, right now in this chart. And what is here in the yellow, let's say, area of the ASIC, it's the embedded RISC processor. On the right side, there is the I3C and SPI interface, and of course, some interrupts. So in case you want to, for example, generate interrupt, if you are above certain level of threshold of acceleration, you can use dedicated pins for it. Let's focus on this ISPU, on this RISC processor a little bit. So we call it ISPU 2.0 because we enhance this RISC processor capability compared to our previous generation of devices. So we are, for example, increasing the program and data RAM up to 32K for the RAM, for the program, and 56 for the data. The core itself is running at 40 megahertz, and of course there is, let's say, many hardware accelerators which you can see inside the core itself. So for example, what you can do, there is a dedicated square root engine which you can benefit from when you are programming your own algorithm, which you can, by the way, program in traditional C code. So what we are delivering with our sensor is a tool chain with a compiler. So you basically program your own algorithm, and there is a way how to get it running on the core, storing the program in the RAM of the device, and to have the program data in the data RAM. The device is also supporting the floating point unit calculation. Now you may ask me why this RISC core is, let's say, beneficial versus something which could run externally in the microcontroller. So I prepared one chart which is showing, let's say, the calculation of the FFT. So if we compare the code which would run on traditional Cortex-M4 or inside the ISPU, we are significantly reducing the number of kilogates. So the code is more dense. We are occupying less memory. So you can also save the memory of your microcontroller, for example, when you run it on the ISPU directly. And in terms of cycles, it's comparable. So the speed is similar. Here is a list of some libraries which we are preparing, ready to use for our customers. And basically, you are not forced to program them yourself. You just select them from our offer, and you run them in the ISPU. So this is one of the options we are also providing to our customers. OK, now I suggest to have a small look on our demo, which we have on our booth. And it is a demo which is showing our sensor in action. So this is the sensor. We have a bearing set up on the motor. And we are, of course, spinning the motor. And we are simulating the failure of the bearing by piezo actuator. You will see later on that we are intentionally generating some frequencies. What you can see in the GUI is the FFT, so the frequency spectrum calculation, and the time spectrogram. The peak in the chart is showing the first vibration frequency, which I am now changing. And you can see in this spectrogram that the peak frequencies are moving as I am increasing the generated, let's say, tone by the piezo actuator. What is the beauty of this? That is that you can run this FFT inside this sensor as well. So it's not only in the microcontroller or in the GUI I am showing here. And again, I invite you to come to our booth, and we can show it to you live. Now, I am approaching the last section of my presentation, which is about the tools. So, of course, you would like to, let's say, develop something with our sensor. So what we are offering is a set of demo boards. So you can see some of them here. We are also providing for free so-called MEMS Studio. It is the GUI I was showing on the previous slide. And we have also some set of, let's say, tools which are also touching AI algorithms, which you could run in the ISPU. So, for example, you would like to have some classification in the neural networks. You can do it. You can run them in the ISPU. It does not need to be only the FFT calculation. So for the C language level programming, we are offering dedicated IDEs. But what I have here in this chart is the way how you could program, for example, some neural networks for the ISPU. So what we are offering are few tools. One of them is the MEMS Studio, in which you can, let's say, generate the C code for the neural networks. And this STH-AI Core, let's say, tool is here to, let's say, convert typical neural network models into ISPU optimized size of code that it fits the RISC core. Besides this, when you want to integrate your neural network library, there is a dedicated toolchain, which we have on our website, again, for free, and you can touch it. And of course, you can also integrate the code inside your own project. Last part was a little bit touched also by my colleague. It's about the amount of data and, let's say, calculations of similar things like FFT or AI inside cloud. So basically, in case we would go to cloud, we would need to stream all data from the vibration sensor, which is a huge amount of data, and it does not make sense. It's not power efficient, and you don't have endless bandwidth in your systems. You can calculate, for example, the AI on the gateways. So you are just passing from the sensor to the local gateway the data. It's also possible. But what I am offering you with our sensor is the calculation of the data directly in the sensor, which is, I would say, very, very convenient, because you don't need then to push a lot of data out. Impact on the maintenance strategy. Okay, typically when you are checking the, let's say, correct behavior, for example, of the motor, you should go with some inspection machine to check the motor one day to another. What we are offering you is early detection, because we are integrating the sensor, for example, in the bearing. We are offering you reduced emergency stops, because we see the signatures of the potential failure much earlier. Less people to come on the site. And of course, with integrated circuit, so the digital MEMS and the processing inside the sensor, you need less electronics on your PCB. So this is the end of my presentation. And this is also the last video, which is concluding on what I was just saying, highlighting a little bit again our sensor. During the video playback, I again welcome you on our booth, which is in the opposite direction of this hall. And my colleagues or me, we will be happy to meet you there at booth number 314. Thank you very much for your time.
Well, thank you, Vladimir. And we have some time left. You were perfect in time. So are there any questions immediately? Yes.
Hello. Thank you for the very nice presentation. You touched on the subject of battery, but didn't really come back to it. Do you also have to have a battery inside the bearing? And then does that then limit the lifetime that you can actually measure?
Okay, I don't hear you well, to be honest.
A bit closer. Hi, sorry. Better?
Yeah, better.
Yeah, you touched on the subject of battery, but you maybe didn't come back to it. Does that mean you have to have a battery inside the bearing as well? And
correct,
then
correct.
that limits the lifetime of sensing, or?
Yeah, you need to have also the battery. Okay, we are not creating, let's say, the electronics for the bearing. I mean, our company is the semiconductor company, but there are companies which are specializing on this. And of course, in the system, typically you need the battery, you need some RF communication, you need a sensor to measure the vibrations, and also typically you have there also specific wake-up sensor. So typically there is also, let's say, very, very low power accelerometer on top, which is drawing, I don't know, less than a microamp when it is running. And you basically use it to wake up the system in order to save, let's say, the power on the system level.
Any other questions? No, so if you need more information, I have other questions, then the booth is there, 314, which must be near to the entrance, I guess, from the...
Correct, at the entrance.
So, thank you, Vladimir.
Thank you.
And our next speaker is already there, yes. And so we have a short break, and then we will continue.